Cool. So it's kind of an interesting week. So we're on week 6 on our way to week 7. Week 7 is when the second exam is. It's on the Thursday of that week. So after we finish content for today, that's where we're going to draw the line in the sand for new material for the test. So after today, the stuff that we would cover on Wednesday, that would be stuff that is not available for testing, at least for the second test. Because it's electrochemistry, and not that it's hard or anything, it's just that we're not going to have a whole, I'd much rather keep that on its own for a test, because we have 2 topics left, I'm sorry, thermochem, then electrochemistry. So let's keep those 2 topics on their own for a test. So equilibrium is going to wrap up here, at least the way we've been experiencing it. So by Wednesday, you should have a new study sheet that will get posted, and you get an opportunity to go through some of those questions. For those of you that worked really hard on your assignments over the weekend, I'm going to start grading them. So now that I have them all in, and that file will be very useful for you for the coming test. So you're going to want to hold on to that. Okay. Any questions over anything before I get started? Okay, if there's nothing, then I shall close that file, and I'll start sharing my desktop, and we can go from there. Okay, so here we are for class for today. Today we're going over acid-base weak titration with a titration with a weak base, indicators, and solubility. And this is nice. This is a rather challenging topic overall, equilibrium, but it ends on a real easy note with solubility. So we will have a good time with that. Other things I just want to sort of re-mention, we've got your extra credit. It is due Friday. Your homework, it is due Sunday. And quiz on this coming week, I believe it's on the Thursday. So you've got those things coming up. Something in the chat. Will I post it? Oh, shoot. Yes, I will. Here, let me do it right now. Thank you, Megan, for the reminder. I thought I did that. Give me one little second to do that, okay? Thing is, it's not a very big file today, so I should be able to post it pretty quickly. Thank you for the reminder. Come on, internet. I know you can do it. You're welcome. Sorry, I've got nothing to fill the time with. Course contents. And luckily it's a drag and drop too, so one quick sec. 6, this file, 2 materials. Okay, just threw it up there, so it'll be posted in about a minute or so. Thank you so much for reminding me, Megan. Appreciate it. So let's start with the weak base titration. The weak base titration, it works exactly like the titration of a weak acid. The only thing that you kind of have to keep track of is your map. So there's all the same landmarks that you're used to seeing in initial pH, the pH after some acid's been added, the pH at the equivalence point, and the pH after the equivalence point. Those are like the 4 major landmarks that we're going to pay attention to. This other one is here, and we'll look at that as well. It's no less important. That is halfway to the equivalence point. And the nice thing by halfway to the equivalence point is there's going to be a relationship between the dissociation constant and the concentration that we're looking at. The other thing you might notice is that when your curves were drawn, they started here around 2, they sort of went up, curved up, and then went up in an S shape like that. And this is sort of the inverse of that. They're starting here around 11, going into a downward slope, deep down, and then this. So it's the same shape of a curve, just reoriented. So here's our question. Let's consider the titration of a 12 ml sample of about 0.175 molar methylamine with 0.15 molar hydrobromic acid, HBr. We're going to determine these 6 things. The initial pH, the amount of acid we need to reach the equivalence point, pH after 5 mils was added, pH at halfway to the equivalence point, pH at the equivalence point, and the pH 5 mils after the equivalence. If it seems like there's a lot in this, there is, no question about it. However, these are all things that we kind of know how to do. It's just that we've been focusing on acid, so I want to show you that we can do the same thing with the base. So we'll work through this. So same thing transcribed. Here's one of the things I was thinking about this. Several people emailed me about like, where do I find the KAs for these things? We're at a part in chemistry where it's a lot like in first semester, where I didn't have to say and go to the periodic table and get this information all the time. We've introduced enough constants, equilibrium constants, and so on, that you should at this point have the ability to look up in the appropriate table something based on some information. And so if you're given the name of something that is a base, right here, methylamine, and here's an acid, a strong acid, you should be able to go to a table of bases and look this up. And so since this information is not given explicitly in a question, you should be able to look that information up. Your textbook is a good source for this. And so all the problems that we do, they come right out of our textbook. And there's nothing that's going to be given to you that is not available to you in the textbook, either in the appendix at the back or in the chapter. So you're going to want to take a look at those 2 things there. Now, so we looked at the KB for that, but we're also going to need the Ka for it when we have its conjugate acid. So remember, the Ka is the ratio of Kw to Kb, and that'll give us a rather small number, 2.27 times 10 to the minus 11. So first thing, let's do the initial pH. So this is in water, and all we need is the concentration, not moles. So concentration minus some amount of X, some of this forms, some of that forms. And X squared over this concentration minus X, we do our small X approximation. We end up with this as our value of X. Remember, that is the OH concentration. So if you take the negative log of this, you'd get POH, not pH, POH. And that becomes 2.06. And subtracting that from 14 gives us 11.94. So it's relatively straightforward to get, the initial pH of something. So that is item 1 taken care of. How much acid do we need to reach the equivalence point? That's not a question we've answered in this class all that much. It's a general chemistry 1 question, which is basically stoichiometry. If I know the molarity of what I'm working with and how much of it I have, I know how many moles I have. I know it's a 1-to-1 mole ratio between these 2, and I know the molarity of my acid. So how much do I need? And that comes out to 0.0292 liters. Oh, not bad. So 2 of the 6 things down relatively quickly. I want to remember this number for later, about 29 milliliters. For the 5 mils of acid being added, I've arranged this just a little bit differently from the previous examples I've worked, but it's the same idea. I've got a concentration times the volume, which gives me moles. And that's my initial of methylamine. And I've got a concentration times volume for this. Now, I did this correctly. I wrote it incorrectly on this, but it is correct. 0.005 is the number of mils here, so it's correct over here. It's just there's a 0 in the wrong place here. So this comes out to, the difference between these 2 moles is 0.00363. And then this is how many moles of this form. So if I know the moles of my conjugate acid and I know the moles of my base, then I can use a version of the Henderson-Hasselbalch equation to get this. And that version is the POH. You can see here I started to write pH just out of habit. POH, that's equal to the negative log of my Kb. So my pKb plus the concentration of my conjugate acid over the concentration of my base. In a typical Henderson-Hasselbalch, this would be pH is equal to pKa plus log of acid over base. sorry, base over acid. Here it's the opposite. POH is equal to pKa plus acid over base. Again, that gives me 2.67 as my POH. I subtract that from 13, and I get 11.33. The thing you want to pay attention to here is that my initial pH was higher, almost 12, and now it's lower, almost 11. That's what should be happening because we're adding acid to this. And so the number that we get here makes physical sense, which is one of the things you always want to ask yourself. I got a number, did some math. Do it right, how do I know? Does this make physical sense? Yes, it does. Okay. So now at halfway to the equivalence point, we don't even really need to do the math here. At halfway to the equivalence point, these two numbers are equal to each other. Whatever's in the numerator and whatever's in the denominator, making this fraction 1. And if that's the case, log of 1 is 0. So our POH is equal to our PKB. That's what I've got written here. POH is equal to PKB, which is 3.36. Again, that's POH. So I subtract that from 14 to get pH. So 10.64 is what we would get for that at halfway to the equivalent point. So we've completed the fourth thing. Let's go to the fifth thing. The pH at the actual equivalence point. So this again, here's what at the equivalence point, all I have is the conjugate acid. All of my base has been used up. It's all been turned into conjugate acid. So if that's all I have around, it's going to act like an acid, a stronger acid than water at least. And it's going to give a proton to water, reforming the base, and H3O+. So what I need to know is what's my concentration of this stuff at equilibrium? Well, it's a 1-to-1 mole ratio between methylamine and methylammonium. So this is what I start with, and this is what I end with. It's a 1-to-1 mole ratio. So my concentration times the amount I used of CH3 and H2. 1 mole of this forms for every mole of that. And then my new volume that I'm dividing by here is the sum of the two volumes that I added. 25 mils of the original stuff that I had, plus 29 mils of acid that I added. So my volume is now the sum of those two, which is like 54.2 milliliters. Let's see here. That gives me this number, 0.08072. And then I sort of skipped some math, but it's the same idea. That's my initial concentration of this, 0 of this, 0 of this. Some of this goes away, some of this forms, some of this forms. So x squared over that concentration, just like we've been doing 100 times before, is equal to the Ka. This is the acid now. So for the Ka, I need to use this number, 2.27 times 10 to the negative 11. That's where that comes from. All right, cross multiplying and taking the square root, I get 1.35 times 10 to the minus 6. That is my hydrogen ion concentration, or my hydronium concentration, and that is 5.86. Do not need to subtract from 14 for this one. Does this number make physical sense? Yes, it does. The reason it does is because it is lower than 7. At the equivalence point, my major species is a weak acid. And as I have a weak acid, I should have a pH that is lower than 7. Okay. Question 6, 5 mils after the equivalence point. So here I've got my base. I'm keep on adding HBr. I'm making the conjugate acid. And when I've added more of this acid than the base I have, all the base gets consumed. So 0.175 was my original concentration, that 25 mils, that how much I added. This is how much of the base I've added. So 0.015 is the concentration, and then 0.0342, 34.2 milliliters. That's because it took me 29.2 milliliters to get to my equivalence point. We calculated that for number 2. 5 mils beyond that is 34, so 34.2. So that's how many moles of acid I've added. It's reacted with this many moles of base, so I'm left with this many moles of acid. And this is my single biggest contribution of acid. So I'm going to take this number and divide it by my new volume, which is 25 mils of stuff I started with, plus 34 mils of acid. And I'm left with a number of 0.0128. If I take the negative log of that, I get 1.89. Which again, makes sense. My pH should drop precipitously. There's a kid at the door, excuse me. It's fine, I can't just shout. Right, sorry about that. So we're at pH 1.89, and so it should be a low pH because right now we're essentially just adding strong acid to a solution. Okay, but every time we do it, it's getting a little more dilute, so it's going to settle in on a number, like asymptotically approach a number. There's not too many of us here in this, so do any of you have any questions you want to ask? Either unmute yourself and ask, or put it in the chat before I summarize this. So are there any questions you guys would like to ask? Nope. Okay, if you think of any, write them in the chat and I can make sure I can address them either at the end of the class or following. Okay. So let's compare this weak acid and or weak base titration. So if I have a weak acid and I'm titrating it with a strong base, then we got to remember that my initial pH is less than 7, because I have a weak acid. So my initial pH should be somewhere above 0 and less than 7. And I'm adding a strong base to it. And so initially it becomes a buffer. And the way that I can work with my buffer is with my Henderson-Hasselbalch equation. pH is equal to pKa plus log of the base over the acid. Okay. So relatively straightforward. That's what we worked with previously. At the halfway to the equivalence point, my pH is equal to my pKa. At the equivalence point, my pH is greater than 7. And that is because only conjugate base is present, and it's acting like a stronger base than a weaker. All right, so those are the things. We start down here, we curve up, and we line up. We sort of like plateau. So we saw that Monday and Tuesday of last week. Sorry, Monday and Wednesday. Weak base with a strong acid, which we just saw today, the initial pH is greater than 7. So we're starting with a weak base, so our pH should be above 7. And then as we add a buffer, what we're actually determining is the pOH. So our pOH is equal to our pKb plus log of acid over base. So basically, we're comparing these two versions of the Henderson-Hasselbalch equation. pH at the equivalence point, the pH at the equivalence point, not the pOH, but the pH at the equivalence point, halfway to the equivalence point, I should say, is 14 minus pKb. Okay, so I could have said pOH is equal to pKb, but I'm interested in the pH of this. And then finally, the pH at the equivalence point is less than 7. That's because only conjugate acid is present. Okay, that's going to end it for titrations for us. And the only ones we do are weak acid with a strong base or weak base with a strong acid. Weak acid with a strong base is a little more common. You can do weak acid with a weak base and weak base with a weak acid. That's just a lot more math. It's not impossible, but that's where having a computer to do the math for you is actually really beneficial. You still have to sketch it out on paper to make sure you're doing it right. Beyond the scope of what we want to do in this class. Okay, but if you guys remember, in Gen Chem 1, you did titrations and you used a, so it probably looked like this. You used an indicator. Commonly, and even if we were in a normal situation in normal labs, you would use a pH meter. pH meters are something that chemists like you and chemists like me geek out about when we see them in conferences. We're all interested in the things they can do. But basically, there'd be a probe that is in a solution. What's missing from this picture is like a stir bar. So a magnetic stirring plate. And we'd be adding acid in some controlled, adding base in some controlled way. And we're watching the pH of this solution, and it would sort of like level off and then shoot up and then level off again. And the computer would be keeping track of that. And that's the job, that's what the sensor is. And this is how you would actually do, in an analytical lab, how you would actually do your titrations. Doing them here like this with a color indicator is a good way to learn a technique, but not necessarily the best way for you to figure out what is going on. So the indicators that we use, you guys probably remember the indicator you used in undergrad in your first semester course, which was phenolphthalein. Phenolphthalein is something that has a colorless constitution here at low pHs, and then as it transitions through pH 7 to 8, it goes from clear to pink, and then kind of like a fuchsia, and stays that color. So with a color, we figure out what the end point is. And what we're watching is when this first changes color. That's the end point. So the job of an indicator really is when we've added enough acid to react, acid reacts with base preferentially in titration. So if we have an acid in here and we're dropping in base, the acid and base are reacting with each other. When the acid is gone, the base reacts with the indicator. So indicator is added to react with the acid once the base has been consumed. The end point is when the indicator changes color. And this chart right here shows all different kinds of acid-base indicators and where they end up changing their color, at what pH range. So if I'm looking for something that changes its pH, let's say, in this region over here between 8 and 9, there's really only one indicator that's going to work for me. So pH for weak base and strong acid at half is 14. So pH for weak base with a strong acid at halfway to the equivalence point is 14 minus pKb. Yes, weak base, strong acid. 14, yes, 14 minus pKb. That is correct, Jacob. Welcome. Okay, let's see here. So anyway, if I want to do a titration of an amino acid, which is a very common lab for undergraduates to do, they tend to have pH changes in these regions here. So using various indicators, you would miss them. And you want to keep excellent track of this stuff. So using a sensor, like the kind that is shown here, is a much better way to go, and we do it with a computer, as opposed to watching for the lightest color change, because that lightest color change might still miss the change in pH. I believe your homework and your book will show you a couple of questions on what the most appropriate type of indicator to use for various pH ranges. It's just another way of asking where the pH at the equivalence point is for various types of acid-base titrations. So you'll want to take a look at that. Yeah, so typically it's a Gen Chem 1 thing to keep track of these things with acid-base indicators, and then in Gen Chem 2 and beyond, we tend to use pH meters. They're not that expensive, they're like $100 each. So this brings us to another really cool use of equilibrium, which is solubility. You guys might remember from Gen Chem 1, we had you memorize solubility rules. All nitrates are soluble, and cations are soluble, all chlorides except for silver, lead, and mercury, those kinds of things. Well, yes-ish. Those are solubility rules. This is what's behind the solubility rules. This is what makes things soluble and insoluble, not from a chemical conceptual point, but mathematically. So let's say I've got calcium fluoride. It's a solid. I drop it in water. If it's an ionic solid, I should form calcium ions and chlorine ions, chloride ions, right? Both of those. And if I wanted to write a K value for that, because I'm talking about a solubility, I would call it K and SP. Now the SP does nothing mathematically. It just sort of tells me what kind of equilibrium expression I'm working with. So this is a KSP. And solids do not appear in my K expressions. And so this is how I would write the KSP. So calcium and then fluoride, and whatever the concentration of fluoride is squared because I've got two fluorines. And so just writing an equilibrium constant, just like we've done for the past couple of weeks. And in general, if I form a lot of ions, that must mean that my solid is really soluble. So a large KSP, a big number, tends to mean it's very soluble. And a small value of KSP tends to mean it's very insoluble, meaning that I don't have a lot of ions. One or both of these is very small at equilibrium. And as a result, it's not soluble. And so that's when we say something is insoluble, that's what we mean. So back in Gen Chem, where we say silver chloride or lead iodide is not soluble, what it means is that the KSP is very small. So it is only sparingly soluble, if at all. So it's a little white lie. It's not, which isn't even exactly a lie. It's just we made it black or white in that one, and now it's what we can see is that, oh, well, there's a solubility thing to consider. So how do we consider it? So here's a common KSP table, and you can see that for various things here, here's the formulas for them, and here are their KSP values, and they all tend to be pretty small. There's nothing interesting about doing KSPs with very large values because we know they dissolve. But for things that are sparingly soluble, like carbonates, 10 to the minus 9, lead sulfide, 10 to the minus 29. So basically, you know, once something like this forms, it doesn't unform. Lead chloride, we said that lead chloride is something that is insoluble. It's got a KSP that's not that far away from 0 or from 1. So the neat thing about this is that if you did sort of like an ion identification scheme, and you did lead chloride, if the lead chloride solution was warm enough, this actually dissolved because temperature will affect this a little bit. So we actually start to modify some Gen Chem labs because this is soluble enough that it could fool you or give you a false positive. So here's a question that would be asked about, and lead 2 chloride is what I'm going to focus on. Here's a question that would be asked. What is the molar solubility of lead 2 chloride? Okay, so here's what lead 2 chloride would look like if it broke up. Lead 2 chloride would break up into a lead ion plus 2 charge. Excuse me. And 2 chloride anions. That's what it would look like. Okay. So I would need to look up the KSP. Now the table I just showed you, 10 to the minus 5, is what it is. So it's right there. All right. So I know it's KSP value, but what am I actually figuring out here? Well, what I'm actually figuring out when they say molar solubility is I'm figuring out the concentration of these 2 ions at equilibrium. So here's kind of what it looks like. I don't know how much solid I have, and I don't care because it doesn't go into my equilibrium expression. But I do know that when I start, I have no lead and no chloride. As some of this goes away, 1 mole of lead forms and 2 lead of chlorine forms. So at equilibrium, I've got X of lead and 2X of chloride. Okay? So this kind of table you're familiar with. Here's how it looks. KSP is equal to the product of these 2 things, X times 2X squared. Okay? That means 1.17 times 10 to the minus 5 is equal to 4X cubed. So 2 times 2 squared is 4. And then X times X squared is X cubed. So I can solve for this in my calculator, dividing both sides by 4 and taking the cube root. And if you have questions on how to do things like cube root in the calculator, please email me. I'll do my best to walk you through it. So when I go and solve for that, I get 0.0143 molar. That is the molar solubility of this. And what that really refers to is the concentration of lead in my solution, no matter how much lead chloride I add, would be this. And the concentration of chloride on my solution would be 2 times that, which would be 0.0286. So that means that if I have a solution of lead chloride that has a concentration that is less than this, I can probably expect it to be dissolved. So lead chloride would actually dissolve in small enough concentrations. As far as K's go, the math got pretty easy pretty fast. Do you have any questions about this example? I'm going to change it up a little bit for another example in just a minute, but I want to see if you had any questions about this example. Okay, I'll move on. we can look at two different things and see what their relative solubilities are. So relative solubility isn't a new thing to calculate. It's trying to say, is this more soluble than that? How do these two things relate to each other? So let's say I've got magnesium hydroxide, milk of magnesia, MOM. If you've ever taken that, it's an antacid. You would take that for an upset tummy. And look at its KSP, 10 to the minus 13. Iron 2 carbonates. This has a KSP of 10 to the minus 11. So on the surface, this looks like that this is not as soluble as that. I'm sorry, this is more soluble than this is. Iron 2 carbonate is this is off by a factor of 100, meaning that you'd think this is 100 times more soluble than this. But that is just the difference in their KSPs. It's not necessarily how different they are in terms of solubility. So let's look at their solubilities. This exercise, and you may want to go back and do this yourself, if you were to go back and basically do the thing that we did here with each of these are the numbers that you would get. So the solubility of magnesium hydroxide is 3.72 times 10 to the minus 5, and the solubility of iron carbonate is 5.54 times 10 to the minus 6. That means that this is the concentration of these ions in solution. This is the concentration of these ions in solution. And what we find out is that this is more soluble than that by about a factor of 10. This is 10 times more soluble than this is, even though the solubility here is, the KSP here is 100 times smaller. Seems weird, right? When this breaks up, it forms 3 particles, 1 magnesium and 2 hydroxides. When iron carbonate breaks up, it forms 2 particles, 1 iron and 1 carbonate. And the math changes a little bit. This is going to have an x cubed factor in here. This is going to have an x squared factor in here. So the moral of the story is we can't look at 2 different KSP values to determine what's more soluble, because if these don't break up into the same number of particles, it's not a good comparison. So if this had 2 particles and this had 2 particles, then we could compare the 2. Since this has 3 and this has 2, we cannot compare the 2. We have to do a little bit of math to see which one's more soluble. Okay, so that's why it's there in red. Do not compare KSP values if they do not break up into the same number of ions. Okay? Now we can influence solubility in some simple ways. So let's say I had calcium fluoride and I wanted to see if it was more soluble in water or in a solution of NaF. So in the left-hand side here, this is going to be in water, and on the right-hand side, this is going to be in NaF. So in water, my KSP is this. So 1.46 is equal to x times 2x squared. And this x we kind of worked through in a previous slide. So if you need to go back and look and see where those x's come from, this is where they come from. So 4x cubed is equal to that, solving for x, 0.0071. Okay, so if I wanted to dissolve calcium fluoride in water, that's the most I could possibly dissolve. Okay, 0.0071 milliliter. So what about if I had a solution of sodium chloride? Well, if I had a solution of sodium chloride, that means I would already have some fluorine there before I did any dissolving. So my ice table looks different now. So I've actually written it in. So here's my calcium fluoride. Remember, I don't know how much I have. It doesn't matter. Start out with 0 of calcium, but not 0 of F minus. I've got 0.1 molar solution of F minus. So that's how much I'm starting with. To that, I'm adding X of calcium and 2X of fluoride. So at equilibrium, I have X of calcium and 0.1 plus 2X of fluoride. So it changes things. How does that influence my math? So my KSP is equal to X times 0.1 plus 2X squared. And because this is a small number, I can do my small x approximation, which means it's X plus 0.1 squared. And now my math's really easy, because I don't even have to take the square root of anything. So X is equal to 1.46 times 10 to the minus 8. So if this X drops out of solution or drops out of the equation, then my math gets a whole lot easier. And this solubility goes way down. Down, down, down. Okay, it was 0.0071 and now it's times 10 to the minus 8. So there's a big drop in solubility. And really, and you can do the math, and it's not hard math to do, but really it comes from Le Chatelier's principle. If you take a look at this, here's calcium fluoride, calcium fluoride. If I add a bunch of fluoride, equilibrium is going to shift back in the other direction to form more calcium fluoride. So solubility should decrease considerably. So you can do the math, or you can use the Chatelier's principle to sort of figure out, oh yeah, that should go away. We can use solubility as well with pH. So let's say I've got magnesium hydroxide and I'm going to add acid to the solution. Every time I add acid, my H plus, it's going to react with something, not this, because that's a solid, so it can't react with it. It's going to not react with this because that's positively charged as well. It will react with this to form water. So that's basically drawing this out of solution. And as I do that, equilibrium, the concentration of this goes down, equilibrium shifts to the right, and more of this gets formed, making this more soluble. So by decreasing the pH or adding acid, I end up shifting equilibrium to the right and dissolving this a little bit more. There's some really fun demonstrations that we do that look like purple snakes in a solution. I've done that one for science shows. People love it. I like it too. The opposite, if I add base to magnesium hydroxide, I put a bunch of OH in here, that's going to shift equilibrium back to the left because I've increased the concentration of this. So in order to consume it, this concentration has to go down. We're going to make more of this. So equilibrium shifts back in this direction. Again, just visualizing it with Le Chatelier's principle is really helpful. The math is not that hard. It's just a matter of trying to figure out what to do. So what is the solubility of calcium hydroxide when the pH is 4, pretty acidic, and when the pH is 9, pretty basic? So let's focus on this part here first, pH is 4. So here's what it looks like when the pH is 4. I've added 0 calcium, and then my OH concentration is 10 to the minus 10. My hydrogen ion concentration is 10 to the minus 4, so my OH is 10 to the minus 10. H plus times OH minus equals KW. And that's where this comes from. Okay, so to this incredibly small number, I'm adding another small number. Adding these things here together. And I can do my small x approximation, saying adding this is not going to end up doing much to this. So when I go through and figure this out, my x is 4.7 times 10 to the 14th. It's a huge number. That means that at pH 4, this is very, very soluble. Okay, because I've added, the concentration of this is so small, I'm basically just pulling equilibrium to the right. So my KSP, or my molar solubility here, is very, very much to the right. When pH is 9, my hydroxide ion concentration is 10 to the minus 5. So it's, 10 to the 5 different from this. 100,000 times different. Okay, so I'm going to add some of this, add two of this, and so on. And now, again, with my small x approximation, I can get rid of that. And what ends up happening is this becomes 4,700. So there's an enormous drop in solubility. Still kind of soluble, molar solubility, but there's a pretty big drop to 4,700. Okay, you guys, I think you have like one homework question that deals with pH and this. It's something you want to take a look at, but really it's just this sort of thing. Le Chatelier's principle. Adding acid removes base, shifts equilibrium to the right. Adding base shifts equilibrium to the left. And there are some good examples that you can work through to sort of see that. This whole thing falls under something that's known as the common ion effect. And so when you're using ions that are similar to the ions that are in solution, it will change the way that things can go into solution dramatically. Okay? That ends that. So let me start my share. See if you guys have any questions. Jacob had a good question earlier. Are there any other questions that you guys have? Okay, so I'll start putting in, grading and putting in points for the assignments from this weekend. And then we'll have class on Wednesday, who is available on Thursday. The class on Wednesday, we're gonna get into thermochem, so it's gonna be new content that day. This is the end of testable content for exam 2. All right, so stuff that we get into on Monday, we're gonna get into it, but it is not for exam 2. Okay, any questions? Okay, if there's no questions, then I will see you all there. Have a good afternoon.